Just a reminder that you have homework that's due this Thursday. You should start working on them if you haven't. All right, Sam, go ahead. What's your question? Yes, that's a class tomorrow.
Mine was the integral from 1 to infinity of 25 times x plus 1 over root x to the fourth minus x. And you have to use the comparison theorem.
This one?
Yeah.
Let me think of it. Well, let's just take the function in the middle and then try to, I'm going to leave the 25 outside, just focus on this part. And let's identify the function that's bigger than this and smaller than this. Right. So the first thing that when you look at this function, you can either focus on the numerator or denominator, right? If we fix the denominator, just focus on the numerator, we can see that x is always going to be greater or equal to 1, right? So this function definitely going to be greater or equal to 1 over square root of x to the fourth minus x, right? If we just drop part of the numerator, the value of the fraction becomes smaller for positive x greater or equal to 1. Well, this is not going to be very helpful when we try to integrate this, right? Because you still have x to the fourth minus x in the square root, which is not very easy to integrate. Let's look at, you can also write down x over square root of x to the fourth minus x. That's also going to be less than the function that's given. So that's also not very going to be helpful. That's not also, this is not very helpful. So let's look at the other end, see if we come up some easier functions. Well, the first thing that we can do is we can manipulate the denominator, right? Because the denominator is minus x, so we know that x to the fourth minus x is going to be less than or equal to x to the fourth, right? So that means square root of x to the fourth minus x is going to be less than or equal to square root of x to the fourth. But when we put those two in the denominator, the inequality sign will flip. That means 1 over square root of x to the fourth minus x is going to be greater or equal to 1 over square root of x to the fourth. Oh. Sorry, I'm just thinking. I think I just said the wrong thing on the other side. So if we minus number. So we can actually use this and then continue to write the expression, the function that's less than the function that's given. So that will be, it's getting smaller. So each of this is going to be greater or equal to 1 over square root of x to the fourth. This one is going to be greater or equal to x over square root of x to the fourth. Does that sort of help there? So we just end up finding the function that's going to be smaller than the given one. So either of this is going to be less than the one that's given. Yes, that's correct. So you can try to integrate each one of this on the left and then see if you can make a conclusion of the original one. So let me just see which one is easier. So since x is bigger, so why don't we just take a square root of x to the fourth? So this is basically 1 over x squared. This one is x over x squared, which is just 1 over x, right? So the next step is that if we integrate 1 to infinity of 1 over x squared dx, that will be less than or equal to the integral 1 to infinity of x plus 1 over square root of x to the fourth minus x, the given integral. So we're just going to focus on this part to see if this is convergent or divergent. What do you think? Is that convergent or divergent? Based on what we did before, right? If you remember, if I remember well, I believe that this expression, this integral, it's going to be convergent, right? So this part is convergent. Well, if this is convergent, we cannot conclude the smaller, so the area below this 1 over x squared, this area from 1 to infinity, this part is approaching to a finite number. The question is, what about the one that's above it, the original one? This part is x plus 1 over square root of x to the fourth minus x. The area underneath this function, the green one, is this going to be convergent? Well, we can't really draw the conclusion, right? If you remember that if the lower function is convergent, has a finite area, we don't know if the function that's higher than that will have a finite area. So cannot conclude. Based on this function 1 over x squared. But what about the function that the second choice, the 1 over x that coming from x over square root of x to the fourth? This one is also going to be less than the function that we want to compare with, right? Both of them are less than the one that's given. So what about this one? This 1 over infinity 1 over x dx, that's also going to be less than or equal to 1 over infinity x plus 1 over square root of x to the fourth minus x dx. We know that because the function is always less than the function in the integral. But this one, if you remember that, if we integrate that 1 over x from 1 to infinity, this is a 1 over x. We know that this area is just going to keep increasing. It doesn't approach a finite number. It's actually going to go to infinity. So this area goes to infinity, which means the integral, this integral with 1 over x in there, that one is going to be divergent. And then, because the smaller area is going to go to infinity, the bigger area that's above it, again, I'm going to use green here. So that's x plus 1 over square root of x to the fourth minus x. This area is supposed to be bigger than this smaller area that's approaching to infinity, so that this bigger area also goes to infinity. Therefore, the integral is divergent. The smaller integral is divergent, implies that the bigger integral is also divergent. I think I'm right, but double check. The 25, as I didn't even use the 25 at all in this case because it's not very useful. We can just add 25 to each of the integral if we need to, but that's not very useful in terms of comparing the integrals directly. This is actually a very good question. I have not done this question myself yet, except for just picking the question. I'm just thinking if we want to pick a function that's bigger than this function. I'm wondering what the choice will be. I'm pretty sure you can come up with some function, but just remember that you want it to be easier to integrate, right? X cubed minus 1. I think you can somehow come up with some function so that the numerator is a derivative of the x to the fourth minus 1. I think you should be able to do that. 4x cubed. You might be able to make pick a function that's greater than the given function. So that will be x to the fourth minus x, and then the numerator will be 4x cubed minus 1. That will make it easier to integrate. But I don't think that's really going to help you much in this case, in terms of being able to use a comparison test. But just note, need to double check x plus 1 is actually less than or equal to 4x cubed minus 1. Equals 1, x equals 2. I think that is true. So, but I might be wrong. So this is just like a me guessing. If you work on this function that's bigger than the given function, you're probably not going to be able to make any conclusion. But I did not try that. I'll try that later. Any other questions on this problem or from homework in general? When you want to use comparison test, I guess the trick that I always use is take the function given, try to find a function that's smaller or bigger by dropping part of the expression that's already in there, right? So for example, in this example, what I did is I dropped one of the numerator because I know that if the numerator gets smaller, then the overall value gets smaller. And then I dropped the negative minus x in the denominator because when you subtract x, it's actually smaller, but when you drop that, you make it bigger. So kind of like manipulate the function in a way like this, you know, take some part, drop it to try to get the function that's either smaller or bigger so you can compare with a given function. Any other questions on this? Good question. If you have more questions, feel free to ask them tomorrow during office hour as well. But definitely work on the homework. So Jacob is right, there's no quiz this week. There'll be exam on Thursday, the following Thursday. That will be the next assessment. And after that, we have 2 quizzes. And that'll be it. We're almost at the end. All right. Any other questions before we move on?
Yeah, I had a question. It's integral from 0 to pi of 26 times sine squared x over
26 times
sine squared x, and then over square root of x.
dx.
Yep.
What is the question asking?
Just determine if it's convergent or divergent.
Okay. This one, I think, so again, 26, I'm going to drop it. Just look at this part. So sine square x over square root of x. It's from 0 to pi. So 0 to pi sine is, so if you remember that from 0 to pi, sine is always going to be from 0 to 1, right? That's a highest. So you can just, I think in this case, you can just say sine x is always going to be from 0 to 1 for the angle x from 0 to pi. And sine square x, again, that's also going to be from 0 to 1, right? So the function that's to either side of this given function, so basically the idea is that we can just directly divide by square root of x for all terms. And the middle expression is exactly the function we have. So sine square x over square root of x will be less than or equal to 1 over square root of x, greater or equal to 0 over square root of x. So that will be 0 for x is from 0 to pi. The 0, there's not much we can compare. It just, or if we integrate 0, that's just going to be 0. So it doesn't change. So that's actually convergent, right? 0 to pi, but so that's, if this is convergent, if this so this integral is less than or equal to 0 to pi sine square x over square root of x, this is convergent because we know that's just going to be 0. So that's going to be inconclusive, so cannot conclude. Right. What about the other side? So we know that from 0 to pi sine square x over square root of x dx, it's, I'm dropping the 26, so that's going to be less than or equal to integral 0 to pi 1 over square root of x dx. This part, Chris, can you double check? Is it really from 0 to pi?
Yeah.
Yeah. Okay. Yep. Well, if it's from 0 to pi, okay. Got to be very careful here because of the 0 is the number that you cannot put in for x, right? Because square root of x is in the denominator. If you put in 0 there, you get 1 over 0, which is not okay. So this integral, if you want to find it, kind of it's actually from 0 positive, the right side of 0 to pi 1 over square root of x dx, because of the 1 over square root of x doesn't really get to 0. So that's a vertical asymptote. And then that you can write as limit t going to 0 positive, integrating t to pi 1 over square root of x dx, you can write as x to the negative 1/2. That's 1 over square root of x. And then going from here, just we can try to evaluate that integral and then take the limit t going to 0 positive. So 0 is here. And that's x to the 1/2. And then divide by 1/2, that's so 1 over 1/2, that's 2. Evaluate it from t to pi. So that's become limit t going to 0 positive. Put in pi. I'm going to move the 1 over 1/2, that's a 2. So I'm going to put it outside. So this term is 2, but I'm going to bring it outside. So I get 2 there. And then x to the half, plug in pi, so pi to the half square root of pi minus t. So that's t to the half, the square root of t. That's what I get when I plug in those two boundaries. And then we take the limit as t goes to 0 positive. The square root of t goes to 0. We just have square root of pi left. So we get 2 square root of pi, which tells us that the limit gives us a finite value. The limit exists and it's a finite value. So that means the integral that we try to evaluate, this one or even this one, doesn't matter, the equivalent. So those is convergent. And if so, that's convergent. The bigger integral is convergent, and then we can make a conclusion about the smaller integral, right? So I'll let you make the conclusion. If you forget, definitely review what we did. I'll just think about area, right? The integral is convergent means that the area. So pi, let's say pi is here. From, I don't know what the graph looks. Let's assuming the graph looks like this. This is a 1 over square root of x. This area from between 0 to pi, the right side of 0 to pi, that's basically, that's finite if the integral is convergent, right? And then you have a smaller area, the function that's smaller than this function. I'm going to use right here. So that's a sine square x over square root of x. What about this area beneath it? Is it also finite or does it go to infinite? Right, so that's the conclusion there. So you can either use the theorem that we talk about, or just try to relate the integral, give you the area, right, in that interval, and use the area to compare. Does that kind of help? I didn't make the conclusion, but I think you should be okay to do that from here. All right, there's another question with a sequence. So sequence 1, 1/4, 1/2, 1/5, 1/3. It asks to find the limit if the sequence converges or not, right? Sorry, just looking at the sequence. I'm curious, so Julie, can you tell us more about this problem? Because I'm curious what the next terms are in this sequence. Anyone know what the next terms in this sequence? So they're asking, is the sequence convergent? I might have to go back to dig out this problem from the homework to look at it, because by just looking at the sequence, I'm not very sure what the pattern is. One is 1 over 1. The next terms are 1 over 6, 1/4, and 1/7. It's supposed to be a homework question. All right, so I'm just thinking about it because I haven't done this yet. 1/2, 1/3, 1/4. Those definitely getting smaller. And then 1/4, 1/5, 1/6, 1/7. They're also getting smaller. Okay, I see now. Good. So I'm not going to be able to really show a lot of details by just looking at it. So the blue sequence, it's always getting smaller, right? As n goes to infinity. So let's just say n goes to infinity. So the blue term, the green term, and then the blue term. Let's just say this is n. N equals 1, n equals 2, n equals 3, and so on. N equals 4, n equals 5. So the blue sequence, the denominator is always getting bigger. So that's going to increase. I might have to come back to this problem later, but so just the blue sequence, the denominator is getting bigger as n increases. So that's going to go to 0. The green sequence that goes from 4, 5, 6, 7. That's also going to go, the denominator also increases, right? It's also going to go to 0. So I'm going to guess, because I'm not sure about this particular sequence, I'm going to guess that the sequence does converge. But is the limit going to approach 0? I'm not sure. I have to think about this. Looks like the limit is approaching 0, but I'm not confident. So 1, 1/4, 1/2, 1/5, 1/3, 1/6. So both sequence is going to sort of getting smaller and smaller over time, and so looks like it might be approaching 0, but I have to double check on that. Good question. Sorry, I cannot give you a definite answer here. Good question. Anyone else? Anyone has a better explanation for this problem? For this sequence, this problem on sequence? All right, so Ryan has a question. So AN is equal to 4 to the n divided by 1 plus 9 to the n. And then we want to know if this sequence converges or diverges, and then limit, obviously. For this problem, the way I'm looking at it is that as n increases, so as n increases, let's see n equals 5, right? So if n equals 5, you have 4 to the 5th and a 9 to the 5th in the denominator. The 1 there is so small compared to 4 to the 5th. So the 1 you can basically neglect. Because compared to the other two terms with the n as an exponent, 1 is very small, so we can basically neglect that. So we basically want to know limit n goes to infinity of an that's about limit n goes to infinity of 4 to the n over 9 to the n. That's what we want to compare at the end. And this one you can write as limit n goes to infinity 4 over 9 to the n's power. And that is going to be, well, I'm just going to use this estimation. So that's a 4 over 9 to the infinity. So what is that going to approach to? Well, this part you kind of have to, it's a lot easier if you just think about the fraction 4 over 9, right? So think about this. 4 over 9 is going to be less than 1, right? And the 4 over 9 squared is always going to be less than 1 squared, which is 1. If you change it to cube, it's always going to be less than 1 cube, which is 1. So it doesn't matter what the exponent of 4 over 9 is, it's always going to be less than 1. But what is it approaching to, right? Then you have to kind of think about, if you have 4 over 9, you multiply by itself, that's going to be 16 over 81, which is a lot less than 4 over 9. Because any number that's less than 1, if you square it, you actually get smaller, right? And then 4 over 9 cubed, I don't know what that is, but if you calculate that, that's going to be a lot less than 4 over 9 squared, a lot less than 4 over 9. So as you increase the exponent, the value is actually getting smaller and smaller each time as you when the exponent increases. So 4 over 9 to the infinity as an exponent, that's going to approach a 0. So that's the limit of that sequence. So yes, it does converge in this case. Okay. I'm sure some of you still have more questions. Any question about this particular problem that I just went over? If you have other homework questions, I'm not going to have too much time to go through it today because I do have to move on to the next section, but I recommend that you ask your question tomorrow or come to my office hours. Any questions on this problem right here? So somewhere in the internet, I found out that if the numerator has a higher power than the if the numerator has a higher power, if you have an equals n cubed over n squared, yes, that's going to convert. That's going to be divergent sequence. But if you have an, I'm going to be careful here. An equals n cubed over n cubed. Well, that's, let's see, n cubed plus 1 n cubed plus n squared. If you have something like this, the numerator, the degree of the numerator basically is the degree, it has same degree as the denominator. This one, I believe, is not going to be, let's think about it. I believe this one is convergent because the limit is a finite number, is 1. Right, so you have to be, yeah, have to be a little bit more careful. Can't just I guess if the degree is the same, then that will be convergent. Same thing if you have a degree that's less, it will be convergent. Because if you have a degree that's less, n cubed plus 1 over n to the fourth plus n squared, I'll just n to the fourth. This one is going to approach a 0. No, when you have problem like this, you should show some work. Like for example, let's just say you have this problem, right? What you should do is you should write down the limit n goes to infinity, an, which is n cubed plus 1 over n cubed plus n squared, and then divide by n cubed to both denominator and the numerator. That's the leading term, the highest exponent term. So that's a limit n goes to infinity of n cubed over n cubed plus 1 over n cubed divided by n cubed over n cubed plus n squared over n cubed. And then take the limit from there. Whatever the limit you get, that will be the limit. Good question. So it was like, anyway. So if you have more questions on this, let me know. I really have to move on. Sorry, don't have too much time to go through the homework questions. All right. If you have questions, definitely ask me at a different time. So the next thing we're going to talk about is 11.2 on series. So we talked about sequence before. Sequence is a list of numbers, right? A series is so definition. A series is a sum of a sequence. So if you take a list of numbers, you add them, add all the numbers in all the elements in the sequence, so that will be a series. It's just a sum. And for example, you can have 1 plus 2 plus 3 and so on. You could have infinite elements, or you can just say, oh, I want to add finite number of them. But generally a series, it's we talk about infinite elements. It should be not always infinite, could be finite, but for now we talk about infinite because we talk about converges and diverges. And let me use a different notation. So notation wise, a series we can write as A1 plus A2 plus A3, and so on with A1, A2, A3, AN. Those are the elements in a sequence, but we're adding them together. So that's a series. So that's a summation notation. But we can also write it using sigma notation, which is, basically is an E. This is sigma notation. And in here, if you remember, that's just going to be the formula for each element. And in this case, the formula I don't know, but I'm going to call it AI, where AI is just individual elements in that in the sequence that I'm adding together. And for I, because I'm going from 1 to 2 to 3 to n and I keep going, so I will be going from 1. So if I put 1 for I, A1, so that will be the first element in my series. And since I'm adding infinitely many of them, so I'm going to put infinity there. So this is what we call the sigma notation. And then this is just the series as a sum. I should be a little bit more careful. Earlier I said summation. The sigma notation is also sometimes we call the summation notation. So that's the notation wise. And then the next thing we want to talk about is called partial sums. The series, we usually use S to represent the sum. But if we don't want to add all the elements in that series, if we just want to talk about a few of them, for example, we can just add the first two together, like A1 and A2, we can add them together to get a sum. So that will be what we call a partial sum. Basically, we take part of the series and add them together. So partial sum, so S2. So that just means we're going to add the first two elements in that series. So that will be A1 plus A2. S3 means we're going to add the first three elements. So A1 plus A2 plus A3. And then you can increase the number. So Sn just means we're going to add the first n elements. So A1 plus A2 plus A3 plus plus An. Note that in that infinite series that we have, An is just an element in the middle. So it's in the middle of that series that we're adding. So there's a lot more elements coming after An. But Sn, this is a finite series with An being the last element. So we add A1 all the way to An. So there's no element coming out of this in this Sn notation. And then S1 is just we're adding the first element to just A1. We're not really adding anything. So all of those are what we call partial sums. It's just a section of that series that we trying to add and find the value. You probably all saw this before. The next part is that, so note from partial sums. So if we just look at S1, S2, S3, all the way to Sn, if we look at each of this value, suppose we can find the value. And if we just look at those values, S1, S2, S3, all the way to Sn, those values, when we write them as a list, the partial sums, when we take them and arrange them as a list of elements, that give us a sequence, is a sequence. So it's a sequence of partial sums. And we usually use a notation Sn in a curly bracket to represent that sequence, with n equals 1 to n. It's not a good notation, but n goes from 1 to 3 all the way to n. So the sum, so in that series, A1, A2, A3, all the way to, I don't know, all those elements, they are coming from a sequence. We add them to get the sum, the series. But if we just look at partial sums, if we take A1, that's S1, A1 plus A2, that's S2, A1, A2, A3 added, that's S sub 3. So that's a partial sum of 3 elements, and so on. If we take the partial sums, put them together as a list of elements, we also get a sequence. So just if you're not familiar with this, definitely review this definition and the terminology. So this is every time you see curly bracket with Sn in it, think about that's a sequence of partial sums. And following that is theorem, if the sequence, it's more like a definition, not a theorem. If the sequence of partial sums, so all the elements S1, S2, and so on, and we note this notation Sn, that sequence, if this sequence is convergent and the limit n goes to infinity of Sn, so the Sn partial sum, as n goes to infinity, exists, and so exists as a finite value. So let me highlight this. So if this partial sum, if that sum approach to some finite value as n goes to infinity, then we say that the infinite sum, the series infinite sum I equals 1 to infinity, AI is convergent. So this definition is a bit complicated. In order to see a series, so this is a series. In order to say a series is convergent, by definition, the partial sums, the sequence of the partial sums have to be convergent. And also the limit is a finite number. So that's two parts. So I'm going to just leave it there. Because if I try to explain more, I might get myself confused there. But try to kind of think about this a bit more. And then I'm going to use a few examples. Hopefully that will help. If the sequence of partial sums Sn is divergent, also includes the case that the limit Sn does not exist or is infinite, then we see that the series is divergent. I'm going to use an example here quickly to kind of hopefully will help understand. So for example, consider the series summation 1 over n going from 1 to infinity. So this is a series. Is it convergent or divergent? This series, I actually wrote it earlier. If you're not sure what it is, let's just expand it. So this series n equals 1. I'm using n here. It doesn't matter. You could call it k. Right? It doesn't matter what it is. To infinity, 1 over k. So if we expand it, so that'll be just plug in 1 first. So that's a 1 over 1. Plus, it's always adding. Plus, plug in 2 there. So I got 1/2. Oh, no, that's not, sorry, this is not what I'm thinking, just k, my fault. I don't know what I was doing. We can talk about that one later, but let's just keep k there, not 1 over k. So if we expand it, put 1 there, we get 1, put 2 there, we get 2, put 3 in there, put k, we get 3. So we saw this series earlier, and then just keep going, right, all the way to infinity. Is this a convergent or divergent? Well, I don't know yet. Well, let's just look at the partial sums. So partial sums. The first partial sum is just S1, so that will just be the first element, 1. The S2 will be the first 2 elements added, so that's a 3. And the next partial sum, S3, so there'll be 1 plus 2 plus 3, so that's going to be 6. And S4, so that will be 1 plus 2 plus 3 plus 4, so that will be 10. So those are partial sums. So if I'm considering the sequence of the partial sums, so consider the sequence 1, 3, 6, 10. The next one I believe is 15. So if we consider this sequence, is this sequence convergent? Because if that's convergent, the limit is a finite number, then the series will be convergent by definition. That's what it says. Is this convergent? Well, just based on just intuitively, right? That the elements is actually increasing by multiple integers each time, by multiple units. So the elements go towards infinity. So this is a n equals 1, n equals 2 in this sequence, n equals 3, and so on. And then that's going to go towards infinity. Therefore, this sequence of partial sums is not convergent. So this sequence of partial sums is divergent. If the sequence of partial sums is divergent, then the series that we want to know earlier, therefore, the series that we're considering, k going from 1 to infinity of k, that one, or you can write as 1 plus 2 plus 3 and then keep going, that series is divergent because of the sequence of partial sums is divergent. Therefore, the series that we're looking for is divergent. So that's what the definition says. I hope it helps. And if that, if the partial sums converges, then the series is also convergent. Any questions on the definition or this example? So that's series being convergent or divergent. Then I'm going to go through a few more examples soon, but let me continue with this notes. So properties. So if series are convergent, there's a few properties. So properties of convergent series. If the series an with n going from 1 to infinity and the series bn with n going from 1 to infinity are convergent. then if the series, those, how can you tell that it's divergent? Divergent basically means that when you, a series, so let me kind of give you a more intuitive definition of a series that's divergent. It basically means that the sum is going to go to infinity. Right? How can you tell? Well, the example I'm using, so by definition, to show that the series is divergent, you have to look at the sequence of partial sums. And then look at that sequence, see if it's divergent or convergent to decide if the series is convergent or divergent. So that's what I did. I took the series that I want to know if it's convergent or divergent. I took it, I expand it as a sum, and then I find the partial sum. So I find S1, S sub 2, S sub 3, and S sub 4. That will give me a list of sums. So those are partial sums. So then I'm taking those sums, I'm going to put it as a sequence, and I'm looking at them and just try to figure out if this new sequence, the sequence of partial sums, if that sequence converges or diverges, right? And it turns out that this sequence here, in this example, going the elements going from 1 to 3 to 6 to 10 to 15, as the number of elements increases, the value of those elements, they also increase, right? You're just going to keep growing. So that tells me that this sequence has a partial sum that's going to be divergent. So those elements, because they increase, for example, it increased by 2 units first, and then by 3 units, by 4 units, by 5th unit. So as it keep going, the increment will be, you just keep growing, right, by a lot each time. So that sequence is divergent. Therefore, the series that I'm looking for is divergent. There's a couple of questions. Is it divergent if the partial sums just don't have the same difference or factor? Even if it has the same difference, so I wouldn't jump into the conclusion of having the same difference or same factor, because soon you're going to see that even if they have the same factor, it could still be convergent. I'll show you an example on that. And also have the same difference. I think have the same difference usually means usually it's divergent. The same factor, it depends on the factor, right? If the factor is more than 1, if it's multiplied by 2 each time, so the value will increase by 2 each time, so that it's not going to approach a limit. The sequence of partial sum is not going to approach a finite value, it's just going to multiply by 2 each time, it's going to infinity. But if the factor is 1/2, then that's different. So I wouldn't try to make a conclusion there. Right.
So since it's just leading to infinity, that's why it's divergent.
Correct. So the values in the sequence here, like if we just keep going, if we just keep making the sequence longer, right, by finding more partial sums, and then you would notice that the elements were just approaching infinity. So that sequence doesn't have a limit. That's a finite value. So that sequence is going towards infinity. Therefore, the sequence we see the sequence is divergent, right, from previous section. And because that's divergent, therefore, the series that we're looking for is divergent. That's what it says here in the second part. If the sequence of partial sums is divergent, then the series is divergent. It definitely takes a lot of practice to try to get your head around this kind of topic. Trust me, just keep trying. And eventually you're going to have a much better understanding on this material. Practice. So let me keep going. And if you have questions, I'll stick around a little bit later to answer more questions. So let me keep going here. So I'm going to turn on my lights. So when you have two convergent series, then there's a few properties. The first one is that if an and the series an and the series bn are both convergent, then if we multiply by an with the constant c, this new series, that one is also convergent. So if every element an is it's multiplied by a constant c, then that new series is convergent. And then we can pull the c out of the summation notation. So and this c times an series, we can bring the c outside. So that becomes c summation an. I didn't write down the index. N equals 1 to infinity, n equals 1 to infinity. So the c, we can just bring it outside. The second one, if we add the series an with n going from 1 to infinity with the series bn and going from 1 to infinity. Because each of them is convergent, then when you add them together, the sum is also convergent. And we can write them as we can combine those two sums just by adding an with bn together and then take the sum of everything. So those are just properties of series, of convergent series. I just want to point out one thing, be careful here. So note, if we multiply the two series, you cannot multiply the elements together. Note, series an times series bn is not equal to the series of an times bn. This is a note. Be careful here. So it works with sum and it works with difference. So if you have an minus bn, that's a subtraction. So either plus or minus, but it doesn't work with multiplication. So those are just properties of convergent series. Let me give you more example on the material that we had earlier. So consider this series, which is 4 plus 16 plus 64 and continues. So this is the example of if you look at elements that we're adding together, they have a common ratio, right? So there's a common ratio. So we multiply by 4 each time as we add more elements to it. But if this series converges or diverges? Well, let's find out. I want to take kind of like a digress a bit here because this series have the elements has a common ratio. So we multiply by 4 each time as we move on to the next element. So this, we have a special name for this type of series. So this is called geometric series, which is the elements in the series has a common ratio. That's a trick to figure out the sum directly. So let me just use this example, try to show you what the sum is before we talk about being convergent or divergent. So suppose the sum is S equals 4 plus 16 plus 64. And then the last element, I don't know what it is. So I'm just going to use the value, the variable n. So I'm going to, this is a 4 to the first power. This is a 4 squared. This is a 4 cubed. So the element, the last one, I'm just going to call it 4 to the n, but keep in mind that n goes to infinity, right? We're talking about infinite series here. And in order to find the sum of this, so this is the S, that's what I'm looking for. So what I'm going to do is I'm going to take that series, I'm going to multiply by the ratio, which is 4. I probably shouldn't use 4, but I already choose 4. So I'm going to multiply by the ratio. So ratio is 4. So I'm going to multiply with S, so multiply by everything there. So when I do that, 4 times S, so that will become, I'm using a black color then. 4 times S is 4 times 4 plus 4 squared times 4 plus 4 cubed times 4. And then all the way adding to 4 to the n times 4. So if we multiply every element in that series, in that sum by 4. So that becomes 4 squared plus 4 cubed plus 4 to the 4th, and all the way adding to 4 to the n plus 1. But if you're familiar with this, the element before that will be 4 to the n. That's the element before 4 to the n plus 1. This is a 4s, 4 times s. Right? And then the next step is I'm going to subtract 4s from the original series. So s minus 4s on the left. So that will become 4 to the first power minus 4 squared plus 4 squared minus 4 cubed plus 4 cubed, if you follow me there. Or let me take 2 steps. Let me write down 4 to the first plus 4 squared plus 4 cubed, and then plus 4 to the n minus 4 squared plus 4 cubed plus 4 to the 4th plus 4 to the n plus 4 to the n plus 1. And if we do the subtraction, we end up with 4 to the first power minus 4 to the n plus 1. Because all other elements are canceled. And then the left side, we can take out s, becomes 1 minus 3. And then we can divide by 1 minus 3, which, sorry, 1 minus 4. We can divide by 1 minus 4. So we get S equals 4 to the first power minus 4 to the n plus 1 divided by 1 minus 4. That's how we get the sum, the total sum for geometric series. Now, let me do couple more steps, and then I'll write down the general formula. So in the numerator, I can take out a 4, becomes 1 minus 4 to the n. The denominator, I get 1 minus 4. But it's a bad example here because I use 4 in both places. But let me just label this. This 4 is the first element of that series. So first element of series. And then this 4 and then the 4 below that I'm boxing in purple, those are common ratio. Normally we use R for the common ratio, and then the first element we usually call it A. Then the general formula for the sum of a geometric series. So that will be just the A, the first element, times 1 minus R to the n divided by 1 minus R. So you probably saw this in high school or a different class in the past. So that's the sum for geometric series. And obviously, if this sum, so if we take the limit, so if limit n goes to infinity of a 1 minus r to the n 1 minus r goes to finite number. So if the limit exists and it's a finite value, then the series, the geometric series is convergent. This is only works for geometric series. So after this step, I just divide by 1 minus 4 on both sides, and then I factor out a 4 from the numerator. So the first step is divide by 1 minus 4. The next step is take out a 4 from the numerator. Well, we're subtracting, right? We have this series is the one that we're looking for. And this is a series is 4 times that, the ratio times that series. And I'm just subtracting. I'm taking 4 to the first power plus 4 squared plus 4 cubed, and then minus 4 squared minus 4 cubed minus 4 to the 4th. So all the terms in the middle, the 4 squared minus 4 squared cancel, 4 cubed minus 4 cubed. And all the terms that I didn't write out, they cancel. 4 to the n also cancel with 4 to the n. And then in the first parentheses, the only element left is 4 to the first power. The second parentheses, the only element left is 4 to the n plus 1. So I get 4 minus 4 to the n plus 1. Well, we multiply by 4 because that's the ratio, right? So if we multiply by the ratio, then we can have a lot of elements cancel out after we subtract. That's why we use. Well, Sam, I didn't write 4 to the 4 because in the first parentheses, I also have 4 to the 4, isn't it? So that cancel is 4 to the 4. There's a lot of elements in the middle. I'm not writing them out yet, but they all cancel with the elements in the second parentheses. So like I said, the only elements left is the first element from the first parentheses and the last element from the second parentheses. And we always, this technique always multiply by the ratio. Whatever the common ratio is, you multiply with it, and then you subtract. Terms in the middle will cancel. Anyway, so let me keep going here. It turns out that for geometric series, the only time that the limit of the sum as n goes to infinity, the only time that goes to finite value is when I is less than 1. So when r is less than 1, s equals limit n goes to infinity of a 1 minus r to the n 1 minus r. This expression, this limit, will approach to finite value. And if you're not sure, just pick random r values, put in there, see what happens. And when r is less than 1, this term as n goes to infinity, if you take a number less than 1, you raise to the infinity power, that will go to 0. We have seen that earlier. So this part goes to 0 when I is less than 1. So s is just equal to a over 1 minus r. So that's the sum for r is less than 1. And when r is greater or equal to 1, s equals limit n goes to infinity, a 1 minus r to the n divided by 1 minus r. This sum is not going to go to a finite value, it's going to go to infinite value. And the series will be divergent. And when I is less than 1, the series is convergent. So you can look into the book. It's all, the formula is also in the book. Right. So whenever we have a geometric series, we can just just compare the r value without going through the partial sums. For example, well, we didn't finish the example earlier. So example earlier, 4 plus 16 plus 64 plus this series, we did not finish earlier. This series we already talked about, it has a common ratio that's a 4. So common ratio r is equal to 4, and that going to be greater than 1. We know that for sure. Therefore, the series is divergent. And if we want to know what the sum is, it's just going to go to infinity, because if we write down the formula, s equals limit n goes to infinity, a is 4, the first element is 4, I is also 4, negative infinity, nope, 1 minus 4. So if you take the limit here, this is going to approach to infinity. Because 4 to the n goes to infinity and the denominator is negative, numerator is also negative, so you get infinity. A second example, we have 5 minus 10 over 3 plus 20 over 9 minus 40 over 27, and so on. What about this series? Is this convergent or divergent? Can we find the limit? Can we find the sum? Well, this one, let's just look at, see if it's geometric. Because I'm picking this example, you're probably already thinking it's geometric. So this is a 5/1, right? So from the first to the second element, the denominator is being multiplied by 3, the numerator is being multiplied by 2, and then it's by a negative sign. So it looks like it's being multiplied by -2/3. And then going from the second to third element, the denominator is still multiplied by 3, the numerator is multiplied by 2, and then the negative become positive. So it looks like it's multiplied by -2/3 again. And that seems to be the pattern. So because we increase the elements by a common ratio, -2/3, so R is equal to -2/3. I gotta fix the error I made earlier. Sorry about that. So when I said I is less than 1, it should be more accurate. Absolute value of I is less than 1. So we talk about absolute value here, not just the actual value. Sorry about that. You probably know that already if you've seen this material. So here, the I is -2/3. So absolute value of R is equal to 2/3. That's going to be less than 1. And that's the case, the series is going to be convergent. And the sum we can find, so S equals A over 1 minus R. So A over 1 minus R in this case, because I is less than 1. So that's going to be A is the first number. Remember, A is 5. And then 1 is just 1. I is -2/3. So that's going to be 5/1 plus 2/3. So that's 1 plus 2/3 is 5/3. So 5 divided by 5/3, that's just going to be 1. Sorry, going to be 3. So that's the sum. So if we continue that series and then just keep adding more elements to add infinite many of them, eventually we end up with a 3. I know. I'm sorry. That's the thundering. It's like right next to my ears. I'm sitting next to the window. So that's if you have geometric series, it's a lot easier to determine if it's convergent or if it's divergent. Just look at the common ratio. And it's also easier to find the sum, because for all geometric series, the sum always use those formulas. Any questions on this example? All right, so no question. I'm going to keep going. I know this could be confusing for you if you haven't seen it before, but hopefully you saw some parts in the past. So the next example, it's consider the series sigma n equals going from 1 to infinity, 1/3 to the n minus 1. Is this series convergent or divergent? If it's convergent, can you find the sum? There's a couple ways. You could just expand a few terms, or you can rewrite them, try to figure out whether it's a geometric. Is it going to 0? I don't know off my head. I don't think the sum is going to be 0, but I know what you meant. You meant that the elements in it, you probably meant that this element as n goes to infinity, it goes to 0. That's correct. But if we add all the elements together, it's probably not going to go to 0, right? Because each of them is positive. So let me just write down a few terms in that series. So if we expand this, so we're going to put 1 there first. So 3 to the 1 minus 1 is 3 to the 0. That's a 1. And if we put 2 there, so 3 to the 2 minus 1, that's 1/3. And if we put 3 in there, so we get 2, so that's a 1/3 squared, and so on, right? Now, what is this series a geometric? Well, if we going from 1 to 1/3, that's multiplied by 1/3. Going from 1/3 to 1/3 squared, that's also multiplied by 1/3. So it is geometric. And what is the ratio? The ratio is 1/3, which is less than 1. If the ratio is less than 1, that means the series is going to be convergent. And then what about the sum? The sum, we can just use the same formula we had earlier, which is a over 1 minus r. That's for the case when I is less than 1. You can use the general formula by taking the limit. Same, so if it's a geometric series, if the elements are being multiplied by a constant, could be positive or negative constant, doesn't matter, as long as it's multiplied by a constant, the same constant to the next element, right? That's what we call the ratio. The ratio is the same between two elements in the series. So that will be A. A is the first element, is just 1. And then 1 minus 1/3. And if you do that quickly, you get 1/2/3. You get 3/2, 1.5. That's the sum. I want to show you another trick here that you could see it easily without expanding it. So taking this series, n equals 1 to infinity. And I'm going to rewrite it by rewriting the 3 to the n minus 1. So that's a 1/3 to the n minus 1 become divided by 3, right? So that's what the 3 to the n minus 1 is, but it's all in the denominator. So I can rewrite this as sigma n going from 1 to infinity. The 3 will pop to the numerator. You can still get 3 to the n in the denominator. And the 3, I'm just going to assuming it's convergent. I don't know if this series is convergent or not, but I'm going to put the numerator 3 aside. So the 3, I'm just going to leave it aside. Don't even worry about it because it's just a constant 3. And then I'm going to write 1/3 to the n. And then the 1/3 to the n is the same thing as, leave the 3 aside. 1 I can think about as a 1 to the n. So 1/3 to the n is the same thing as 1/3 to the n. So what this tells me is that by just looking at it, this expression is being increased, has the exponent n, right? So that's actually the ratio. So whatever the expression has the exponent n, so this is the ratio, the common ratio of a geometric series. But be careful, that's the only part that has the exponent n. Everything else is just constant, right? The 3 is a constant. So this is a constant coefficient. If you have this form, you can always make a conclusion that when you see something like a times r to the n going from 1 to infinity, if you have this or some constant different a, this is always geometric. Right, so going back, so 3/2, that's a sum. So 3/2 is a sum. So if we take this series and we keep adding all the elements, all infinitely many elements all together, we eventually end up with the total sum to be 3/2. So that's the sum of that series. Correct. So the A is always the first element of the series. So in this case, A is 1. What is this last set of steps we're doing?
Will you always use S equals A over 1 minus R?
That's if the ratio, the absolute value of the ratio is less than 1. So this always works for the absolute value of R is less than 1. If it's more than 1, then you have to go back to the general formula with a limit. Which is always going to be either positive or negative infinity in that case. It's don't even have to, because if I is more than 1 or less than -1, the R to the n is always going to be infinity.
I'm sorry. For the first example that we did on this, the sum was 1, right?
This example with 5 and a -10/3.
No, the 4, 16, 64.
Oh, that sum goes to infinity.
Okay.
Yeah. You can always think about, right? If you take 4, you add 16, you get 20, then you add 64, you get much bigger number. If you keep adding, you just end up with very, very large sum. So that's going to go to infinity. What is this last set of steps we're doing? I'm not sure what you talk about, which set of steps. Can you be a little bit more specific? Over here, this is just another way, this part, this is just another way to show that you can identify the series as geometric directly without expanding it, by just rewriting in terms of a constant times a ratio to the nth power. Okay, I'm almost done. I really have to finish this, so let me write down the last part. So here's the theorem. I'll try to, I might run over, use a couple more minutes extra after 7:50, but I'll try to finish as soon as possible. So theorem, if the series an going from 1 to infinity converges, if the series is convergent, then the limit of the elements in the sequence an, so the sequence an as n goes to infinity goes to 0. So this means so an is element of sequence and the series. So this is means if series. So if we take the sequence, we add together, we get the series, right? So what this theorem says, if the series, when you add up those the series of the sequence an, if that converges, if the series converges, then the limit of the elements in the sequence an, that will go to 0. the opposite is not true. The converse is not true. So not correct to see the opposite. So I should say this. Let me just note with red. Note if limit n goes to infinity, an equals 0. If the limit of the sequence goes to 0, it's inconclusive. So we cannot conclude that the series n going to 1 to infinity an converges. We cannot conclude this. Let's just be careful with this. It's just one direction. But this other theorem that we could use, if the limit an as n goes to infinity does not exist, or limit n goes to infinity an that's not equal to 0. So if the limit of the sequence doesn't exist, or if it's not 0, then we can actually make a conclusion about the series diverges. So don't get confused. So if the limit equals 0, if the limit of the sequence equals 0, we cannot make any conclusion. But if the limit doesn't exist, or if the limit is not equal to 0, then the series definitely diverges. So this is called the divergence test. I'll give you a couple examples. Hopefully that will make a little bit more sense. For example, earlier we had this k goes to around 1 to infinity. And that, if we expand it, we get 1 plus 2 plus 3 and so on, right? We had this series. Now, in this series, this is what the an is, right? So this is a kind of like an an. So we can look at this. So we can take the limit of k as k goes to infinity. What does that give us? We end up with infinity, right? Which means, so this is saying that, I'm going to use a different color so it doesn't confuse you. So this is saying that limit n goes to infinity, an doesn't exist because it's an infinite value, it's not defined. That's what it says. So this goes, the limit of k goes to infinity, therefore the series diverges. And if you go back to the example we did earlier, if you just take 1 plus 2 plus 3 plus 4 and then keep adding, that sum is just going to grow, going towards infinity, right? So we already know the series diverges. But here, if we just looking at the limit of the element an or k in this case, the limit goes to infinity, therefore the series diverges. So that's how this divergence test works. Another example, we had earlier we had another one, I think was 1 over 3 to the n minus 1 as n going from 1 to infinity. This series, we can just focus on the an term, this one, and we just take the limit as n goes to infinity of 1 over 3 to the n minus 1. What does that give us? Well, again, the n goes to infinity, so that basically becomes 1 over 3 to the infinity minus 1. Infinity minus 1 is still infinity, right? 3 to the infinity is 3, it's infinity. And a 1 over infinity, we know that that's approaching 0, right? So here, the limit of this an formula, the terms that we're adding has a formula 1 over 3 to the n minus 1. That, if we take the limit as n goes to infinity, that's going to go to 0, right? This is not what the divergence test. The divergence test says if the limit doesn't exist or the limit an is not equal to 0, then it diverges. But if we found out that an equals 0 when we take the limit, so here we found limit 1 over 3 n minus 1 n goes to infinity equals 0. Remember that the part I wrote in red? If we found out the limit equals 0, we cannot conclude if that series converges or not. So cannot conclude. Even though previous example, we already found out that it's convergent, but by just based on this, we cannot conclude if the series converges or not. So I just want to draw your attention to that. Even, like I said, we already know it converges, right? We found out it converges because it's a geometric series. We know it converges, but we cannot draw the conclusion by just looking at the limit of this term. All right, I'm going to do one more example, then I'm going to finish it here. Should be done in 2 minutes. I know some of you have to go. So this example, what about this series? N squared over 5 and 5 times n squared plus 4. Is this going to be convergent or divergent? Well, mostly is this divergent, right? I'm going to use the divergence test. So I'm going to focus on this part and take the limit as n goes to infinity. N squared over 5 n squared plus 4. And then that's going to, I'm going to divide by n squared from numerator and denominator. So that's a limit n goes to infinity, n squared over n squared divided by 5 n squared over n squared plus 4 over n squared. And that, since we're already familiar with this, so that's just limit n goes to infinity, 1 over 5 plus 4 over n squared. As n goes to infinity, this just becomes 1/5. It's a finite number, but it's not 0, right? So this 1/5 is not equal to 0. So we found out that the limit n goes to infinity of n squared over 5n squared plus 4 is equal to 1/5, but that's not equal to 0. Therefore, the series n squared over 5n squared plus 4 diverges, or is divergent. So whether it's equal to a finite number, or if it's or if it doesn't exist, or infinite number, as long as the number is not 0, then it diverges. That's what this divergence test says. So the limit doesn't exist, or the limit is not 0, then the series diverges. Okay, so that was the end. Let me answer a question. How do you know when to divide by the highest power in the denominator? I always divide by the highest power from both numerator and denominator. So here I have n squared and n squared, so I divide by n squared. But if you have example, let's see, n squared divided by n cubed, or n cubed divided by n squared plus 4, you divide by n cubed. Our first question. So can we see it converges if it does equal to 0? It's still you still cannot conclude. So if we end up having the limit instead of 1/5, if we end up finding this number to be a 0, it still cannot conclude based on this divergence test. There will be other things that, so that there'll be other tests we can do to try to figure out whether the series converges, or we can look at whether it's geometric series, or we have to use other ways. Correct. It's divergent if the limit does not equal 0. Like in this case, right? The limit is not 0, so it's divergent. The series is divergent, or the series diverges. All right, I'm going to stop. Sorry for taking extra 7 minutes, and sorry for being late. I'm going to let you go have dinner, and I'll see you tomorrow.